In this video, we will discuss about valid arrangement of pairs. You are given a zero index 2D integer array pairs where pairs of I equals to start comma end. An arrangement of pairs is valid if for every index I we have end of I minus 1 equals to the start of I. Return any valid arrangement of pairs. The input will be generated such that there exists a valid arrangement of pairs. So what they are saying is that in the input we are given a 2D integer array pairs. Now we need to arrange these pairs in a format. What is that format? That in each pair, whatever is the ending element, that should be equals to the starting element of the next pair, right? And they are saying that such an arrangement will always be possible, right? So see, if I try to draw all these pairs as a graph meaning this is denoting an edge which is coming from node 5 to node 1. If we try to draw this in the form of graph, then what will happen is, so we have a node 5 and we have a node 1, right? We have a node 5 and a node 1 and there is a directed edge from 5 to 1, right? Then the next pair is 4 comma 5. So we are having a node 4 and there is a directed edge from 4 to 5, right? Then the next pair is 11 comma 9, meaning we have a node 11, right? And we have a node 9, right? And there is a directed edge from 11 towards 9. Then the next pair is 4 comma 6. So we have another node that is 6 and we have a directed edge from 4 towards 6. Then we are having 5 comma 4. So we have an edge from 5 towards 4, right? Then next is 9 comma 4. So from 9 we have a directed edge towards 4. And then the last one is 6 comma 5. So we have an edge here, right? So this is how our graph looks like when we plot these pairs as an edges, right? So now if you see here, they want a valid arrangement where the ending element of a pair should be equals to the starting element of the next pair, right? So if you see, if I start with this node 11 and try to traverse the graph, then what will happen is, I will go from 11 to 9, 9 to 4, 4 to 6, 6 to 5, 5 to 4, 4 to 5 and then 5 to 1, right? So if I just write all this traversal that I did, so it was first from 11 to 9, then 9 to 4, right? 4 to 6, 6 to 5, then 5 to 4, then 4 to 5 and then 5 to 1, right? So now if you closely look, is this a valid arrangement that we wanted? Yes. Why? Because see, this is ending with 9, this is starting with 9, this is ending with 4, starting with 4, 6, 6, 5, 5, 4, 4 and 5, 5, right? So this is one of the valid arrangement of pairs that we are looking for, right? So let me remove this. So what we did was we picked the starting node and we traversed the graph, right? So our traversal was 11 to 9, 9 to 4, 4 to 6, 5 to 4, 4 to 5 and then towards 1. So if you see, in this particular traversal, we traversed each edge exactly once, right? We are traversing each edge exactly once. And such a path in a graph is known as Eulerian path. Such a path in a graph is known as Eulerian path, right? So, in a Eulerian path, each edge of the graph is visited exactly once, right? If you see, here we traversed each edge exactly once and we have covered all the edges, right? So we need to find out a Eulerian path in our graph, right? And since it is given that a valid arrangement will always be possible, then that means an Eulerian path will always exist in our graph, right? Now there is a property of Eulerian path that a starting node is the one where the out degree minus the in degree is equals to 1. So basically, what is the out degree? The out degree of a particular node is the number of edges that are going out of that node, right? And the in degree of a particular node is the number of edges that are coming into that node, right? So for whichever node, the difference between out degree and in degree is 1, that is the starting node in our Eulerian path, right? So if you will see in this particular case, for this 11, its in degree is 0. There is no edge that is coming into 11. So its in degree is 0 and its out degree is 1 because there is only one edge that is coming out of it, right? So 1 minus 0 is 1. then that means this particular node can be our starting node, right? If we see for any other node in the graph, if I consider this 4, what is its out degree? 1 and 2. And what is its in degree? 1 and 2. So 2 minus 2 will be 0. If I see for this 6, in degree is 1, out degree is 1. Difference between them is 0. Right? So basically, the nodes in between will always have the difference as 0. But the starting node, it will have out degree minus in degree equals to 1. Right? If we look at the ending node, so for this, the out degree is 0, in degree is 1. So this is minus 1. Right? So this is how we will be able to identify our start node. Now, let us suppose that there was another pair which was from 1 to 11. Then in this case, what would happen? That we would have an edge from 1 to 11 also. Right? So in that case, this 11, its out degree and in degree difference will be 0. And you will see in this particular case, there will be no node where this condition holds. Why? Because see, if I start from this 11, then what will be my path? I'll go to 9, then to 4, then to 6, then to 5, then to 4, then to 5, then to 1, and then to 11. So I started from 11 and I came back to 11. Basically, my starting and ending node is the same. And when this was not present, in that case, my starting node was 11 and ending node was 1, right? So, if in an Eulerian path, the starting and the ending node is the same, then that is known as a Eulerian circuit. That is known as a Eulerian circuit, right? So, in a Eulerian circuit, if a Eulerian path has the start and end node as the same, then that is a Eulerian circuit. Now, in a Eulerian circuit, we can choose any node as our start node, right? We can choose any node as our start node. So, basically, for identifying our start node, so let me remove this edge now. So, basically, for finding out the start node, what we will do is, we will identify the in degree and out degree of all the nodes, and we will identify that for which node we are getting this property, that the out degree minus in degree is equals to 1. Right? And if there is no such node for which this condition is holding, then we can choose any arbitrary node as our starting node, because in that case we would be having an Eulerian circuit, right? So now, once we have identified our starting node, what we can do is we can simply perform a depth first search, right? And we can identify the path, and that path is going to be our Eulerian path, and with that path we can identify the valid arrangement of the pairs, right? So let us see how are we going to do that. So we will apply an iterative DFS over here. So let's just quickly go through that. So first of all, we would be needing the adjacency list of the graph, right? So we will create an adjacency list, right? In this adjacency list, we will be having all the nodes. So what are the different nodes in our graph? Node 1, 4, 5, 6, 9 and 11. So basically there are 6 nodes in our graph. Then we will update this adjacency list by traversing in our pairs. So from 5 to 1 we are having an edge, that is 5 is connected to 1. Next is 4, 5. So 4 is connected to 5. Then 11 to 9. So 11 is connected to 9. Then 4 to 6. So 6 we will update here. Then 5, 4. So we will add 4 also here. Then 9, 4. So we will add 4 here. Then 6 to 5. So we will add a 5 here. So this is how our adjacency list is going to look like, right? And now for identifying the starting node, we will also have to identify the in degree and out degree of all the nodes, right? So we will find the in degree and the out degree. So the nodes are 1, 4, 5, 6, 9, 11 and here 1, 4, 5, 6, 9, 11. Right? So initially the in degree and out degree of all of them will be 0, right? Then from the first pair, there is a node starting from 5 and going towards 1. Then that means out degree of 5 should be increased by 1 and in degree of 1 should be increased by 1, right? So 5's out degree will be increased by 1 and 1's in degree will be increased by 1, right? Then in the next pair, 4, 5. So 4's out degree will be increased by 1 and 5's in degree will be increased by 1. Then 11 to 9. So here 1 and here 1. Then 4 to 6. So this will become 2 and this will become 1. Then 5 to 4, so this will become 2 and this will become 1. Then 9 to 4, so this will be 1 and this will be 2. And then 6 to 5, so this will be 1 and this will be 2, right? And these will be 0. The in degree of 11 is 0, there is no incoming edge, and the out degree of 1 is 0, there is no outgoing edge. So this is how our in degree and out degrees look like. Now for identifying the starting node, we will do the difference of out degree minus in degree. So here when you will do, it will be -1, here it will be 0, 0, 0, 0, here it will be 1. Then that means this 11 is our starting node. And if in any of these we are not able to get the difference as 1, then we can choose any node as our starting, right? So in this particular case, our starting node is going to be 11, right? This is our starting node. Now we need to perform the depth first search. So for that we will perform iterative depth first search. So I will be maintaining a stack over here, right? We will maintain a stack and we will keep on pushing our nodes into this stack, right? So we'll maintain a stack. Now initially what we want is, we will start with our starting node, right? So we will push 11 into our stack, right? So once it is pushed, once we have pushed the starting node, then what we do that, while our stack is not empty, we take the top element of the stack or the top node from the stack, and then we look at its neighboring elements, and then we push one of them again into the stack, right? So what we will do is, we will take this 11, so our current node will become equals to 11. Now we need to check that what are the neighboring nodes of this 11, right? So 11 has an edge towards 9, so 9 will be pushed into the stack, right? And since this 9 has been considered now, we shouldn't consider this edge 11 to 9 again, right? So for that we will have to do something so that we do not consider this 9 again, right? So what we can do is that we can remove this 9 from this adjacency list of 11, right? So what you can do is that this adjacency list, the keys you can maintain as an integer and the values you can maintain as a DQ. Why DQ? So that you can pop the node that you are considering from the front. For example, for this first you will be considering 5 and then 6, right? So when you would be considering 5, you can pop this 5 from the front. So only 6 will remain, right? So that is why this adjacency list we can maintain as a map where the key will be an integer and the value will be a DQ of type integer, right? So this is how our adjacency list will look like, right? So this node 9 will be removed from the adjacency list of 11, right? There are other possible ways of doing that. You can utilize this out degree, right? So when you have considered a neighboring node of 11, you can decrease its out degree by 1. So this will become 0. And then this particular number you can take and you can identify that index in this list, and that index you can use here. So with this, you won't be considering that element again or that node again. So there are different ways of doing this. I am doing with the way of considering the list as a DQ, right? So this 9 will be removed from here, right? So now in the next iteration, my current node will be 9. Now again, I will see for 9, I have 4. So 4 will be pushed into the stack and this will be removed from here. Then in the next iteration, my current node will be 4. For 4, the neighboring element is 5. So we will push 5 and it will be removed from here. We are only considering 5. We are not considering 6 because we are performing a depth first search here, right? So now in the next iteration, the current node will be 5. So for 5, we will take this 1 and we will push into the stack, right? Then the current node will be 1. Then we will see for 1. For 1, we are not having any neighboring element, right? Then that means we will remove this element from the stack and we will push it into our result. Basically, the path that we are identifying, in that we will push, right? So if this is the resultant path that we are maintaining, so 1 will be removed from the stack and it will be pushed into this resultant vector or an array, right? Then our next node is 5. For 5, do we have a neighboring element? Yes, we have this 4. So this 4 will be removed from here and will be pushed into the stack. So now our current node will be 4. So for 4, do we have a neighboring element? Yes, we have a 6. So we will remove this 6 and we will push it here. Now our current node is 6. For 6, we have a neighboring node 5, which will be removed from here and pushed into the stack. Then current node is 5. For 5, we are not having any adjacent element. We will remove this 5. It will be added into the result. Then current node will be 6, again no neighboring elements, it will be added here. Then the current node will be 4, no adjacent elements, it will be added here. Then current node will be 5, no adjacent elements, added into the result, removed from the stack. Then current node is 4, no adjacent element, it will be added to the resultant vector and removed from the stack. Then the current node is 9, no adjacent element, will be added to a result and popped from the stack. Then the current node is 11, no adjacent element, we will remove it from here and we will add it in our result. So this is the path that we have got, right? This is the Eulerian path, but it is in reverse order, right? If you see, from 1 to 5, we don't have any edge. This is in reverse order, right? So for getting the correct path, we will have to reverse this Eulerian path that we have got, right? So when we will reverse it, then what will happen? If I remove this, so after doing the reverse, we will get 11, 9, 4, 5, 4, 6, 5 and 1, right? So if I just show this path on the graph, then it is 11 to 9, then to 4, then to 5, then to 4, then to 6, then to 5 and then to 1, right? So this is the Eulerian path that we have got, and through this we can create the pairs. How can we create the pairs? So for the first pair, this will be the starting node and this will be the ending node, right? The first pair will be 11, 9. These two we have considered. Now for the next pair, this will be the starting node and this will be the ending node, right? So 9 to 4. This we have considered. Then for the next node, we will consider 4, 5. Then for next 5, 4 and so on. So it will be 9, 4, 4, 5, 5, 4, 4, 6, 6, 5 and then 5, 1. So if you see, whatever were the pairs that were given to us, we have rearranged them into a valid arrangement where each pair's last element is equal to the starting element of the next pair. 9, 9, 4, 4, 5, 5, 4, 4, 6, 6, 5, 5, right? So this is what we need to do, right? So let's quickly code it out. So first of all, we need an adjacency list, right? So we will create an unordered map where the key will be of type integer and the value will be of type DQ integer, right? We already discussed that why we are using DQ here. Let's name it ADG. So this is our adjacency list. Then we need a map for our in degree and out degree also. So we will create another unordered map where the key will be an integer and the value will also be an integer, right? And we need one for the in degree and one for the out degree, right? So now we can traverse in our pairs vector and update our adjacency list and in degree and out degree. So for auto pair in pairs, right? So the starting node will be pair of 0 and the ending node will be pair of 1, right? Then in the adjacency list at the start index, we will have to push the ending node in the DQ from the back, right? So we will do push back end node, right? And then we will update the out degree of starting node and in degree of ending node, right? So out start plus plus and in end plus plus. Right now we will have to identify our starting node. So initially we can keep it as -1 and then we will iterate inside our in degree out degree, right? So what we can do is we can take each item from out, right? We can take each item from out. So this item will give us two things. First will be the node and second will be its out degree, right? So the node is item dot first, right? So now we have to check that if the out degree of this node minus the in degree of this node is equals to 1, right? If it is, then this is our starting node. So start equals to node and we can break here, right? Otherwise, if it is an Eulerian circuit, in that case, our start will be equals to -1 only, right? So in that case, we can choose any node as our starting node, right? So what we will do is that whatever is the first element in the first pair, that we will consider as our starting node. You can take any, right? Then we need to perform the DFS since we have got our starting node. So first we will create a vector. Let's name it res. So this will store our path that we will get, right? And we need a stack, right? So in the stack, initially we will push our starting node, right? After pushing it, we will run a loop that while our stack is not empty, what you do? Take the first node. So it will be st dot top. So once you have got the top node, you need to check whether there are any neighboring elements of this node or not. Basically, in the adjacency list for this particular node, do we have any other node or not? So we will check that if the adjacency list of this node is not empty, right? If it is not empty, then in that case, we will take the front element. The next node will be the front element of the DQ. So it will be dot front. So basically, in the adjacency list of this particular node, whatever is the front element in the DQ, that is going to be our next node, right? So in the stack, we will push this node, right? And we need to pop it. We need to pop it from the adjacency list also. So adjacency list of node dot pop front, right? Otherwise, if the DQ is empty for that particular node, in that case, we will have to remove it from the stack and add it into our resultant vector, right? So in the result, we will push back the node, right? And we will pop it from our stack, right? So this is how we are going to perform our DFS. Now, once we are done with it, we will get our path in the res vector, but it will be present in reverse order, right? So we will have to reverse it first. So we will do reverse res dot begin, comma, res dot end. Now we have got our exact path, and with this path, we will have to create our pairs, right? So we will create another vector of vector. Let's name it answer, and then we will iterate inside the resultant vector. So we will start from the index 1 while I is less than res dot size, and we'll do I plus plus. Now inside this, in the answer, we will push back. What are we going to push back? Res of I minus 1, comma res of I, right? So basically, for the first pair, resultant vector's 0th index will be pushed here and first index will be pushed here, right? So with this, we will be able to identify the pairs, and at the end, we can return it as our answer, right? So this is our code. So let's quickly run this. So our test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.